Hello, I'm Sébastien Bouchard. My co-authors are Yoann, Dieudonné and Andrzej. I'm going to explain that if you need to gather, then you don't need to chatter. The word gather refers to the distributed task involving mobile agents and known as gathering. I'm first going to present you those mobile agents and the task of gathering. Then I will give more details regarding the model considered in our article and our contributions. These contributions rely on two algorithms. I will give the high-level idea behind the first of them. Let's start with a presentation of mobile agents and gathering. Mobile agents are theoretical entities able to perform computations, execute an algorithm, observe their environment, and move in it. The environments we consider are finite, undirected simple graphs like the one depicted here. On the slides, the mobile agents are represented by this kind of picture. When in a graph, the mobile agents move from one node to another one, following the edges. Several work consider mobile agents and differ in particular in the abilities the mobile agents are supposed to have. We build on a series of work which assume that every mobile agent can only observe its surroundings, that is, the node where it is. It can see how many agents are incident to its current node and their port numbers. Time is discretized into an infinite sequence of rounds. In each round, every mobile agent can choose a port number and traverse the corresponding edge. In the next round, the agent is at the other endpoint of the edge. Every agent is equipped with an unbounded memory. In every round, the choice made by the algorithm can take into account the history of all the previous choices and observations. Every mobile agent can also choose to wait, in which case it just stays idle during the round. And so on. We are interested in deterministic algorithms. I like this because this has important consequences, in particular on the model. In this example, the two agents are at same-looking nodes. If there were nothing different between the agents, then their deterministic algorithm would make the same choice for both of them. For instance, here, the two agents would choose the same port number. The graph is symmetric. The two agents would keep reaching same-looking nodes and making the same choices. In particular, in this graph, the distance between them will never decrease. This is important because, as you may know or have guessed, gathering, roughly speaking, consists in bringing the agents together. This is impossible to achieve in a deterministic way without something to break the symmetry. To do so, we use integer identifiers called labels. Every mobile agent is initially given a label, here represented with the blue border. Thanks to these labels, the deterministic algorithm can give a different behavior to each agent. The series of work on which we build put an emphasis on locality. The agents can only observe their current node, have no idea where the other agents are or how many of them there are. Moreover, the agents cannot communicate with agents at other nodes. However, in this work, the agents can talk when they are collocated. They can exchange an unbounded amount of information. And so on, until achieving the gathering. That is, until all agents are gathered at the same node, and they all declare at the same round that the gathering is achieved. The current state-of-the-art algorithm to achieve gathering in the model I have just described is due to Andrzej. That's it for the presentation of mobile agents and gathering. I'm now going to introduce our model and contributions. We assume that the agents are unable to chatter. Unlike in the previous work, we suppose that the agents are unable to communicate explicitly. However, if this ability were not replaced by any weaker one, the agents would not be able to know whether there are other agents with them or not. Hence, we cannot ensure the termination property. The agents could not declare simultaneously that the gathering is achieved. Hence, we assume that in every round, every agent knows how many agents there are in its node. It should be stressed that the agents do not see other agents entering or leaving their node. They can only see the number of agents at their node. As for instance, an agent will not notice any change if, while it is waiting, one second agent leaves its node and one third agent enters its node. As stated by the title of the article, we have proved that it is possible to achieve gathering in this model. We do so by providing two gathering algorithms. The first algorithm requires that every agent initially knows the polynomial upper bound on the number of nodes in the graph. The second algorithm does not require any additional information. The first algorithm is polynomial in the number n of nodes and the length L-min of the smallest label, which means that every agent only performs the number of edge traversals, which is polynomial in these two parameters before gathering is achieved. However, the complexity of the second algorithm is much worse, since it is at least exponential in these two parameters. As a byproduct to our gathering algorithms, we provide efficient algorithms for gossiping and leader election. Leader election simply consists in electing one leader and making all agents learn its label. For gossiping, each agent initially has a message, and the goal is to make all messages known to all agents. This result about gossiping is perhaps our most surprising finding. Agents devoid of any transmitting devices can solve the most general information exchange problem as long as they can read counters at visited nodes. In the rest of this presentation, I am going to focus on our first algorithm. Before presenting the ideas behind the algorithm, I need to introduce some preliminaries, some tools regularly used in the series of work I have already introduced. These tools are called exploration sequences, XS. These are just integer sequences like 1, 2, 4, 1, 1, 0. They are used to guide the agent through the graph. The sequence is read one integer per round. This integer is used to choose what to do during the round, as follows. When the agent enters a node of degree d, by a port whose number is p, and reads integer I from the sequence, it takes port p plus I mod d. Let's take an example. At the very beginning, the agent has not entered by any port. We take p equals 0 here in green. The agent reads the first integer in the sequence, here 1. It computes 0 plus 1 mod 4, which gives 1. It takes port 1 here in red. In the next round, the agent has entered its current node by port 1. It reads the next integer in the sequence, here 2. It takes port 3. It may happen that the agent takes the port by which it has entered the node, like here. It entered its current node by port 1, it reads 4, and the degree of the node is 4. Hence, it takes port 1, and so on. The sequence I have used as an example is not really interesting. By following it, the agent has not visited many nodes. However, it has been proved that given an upper bound on the number of nodes of a graph, you can build exploration sequences of length polynomial in this upper bound, which ensure to visit every node, regardless of the topology of the graph and of the starting node. Such exploration sequences are said to be universal. Following such an exploration sequence is the first part of the subroutine we call explore, and whose second part consists in backtracking the first one, that is, traversing the same edges but in reverse order and opposite direction. For our first algorithm, the agents initially know an upper bound on the number of nodes of a graph. Hence, when they execute explore, they visit every node of the graph at least twice, once during the first part, and once during the second part, which consists in backtracking the first one. Moreover, at the end of the backtrack, they are back at the node where they started executing the subroutine. That's it for the preliminaries. I'm now going to present the high-level ideas of our algorithm. Every execution of our algorithm can be viewed as a sequence of steps. At the beginning of the first step, the agents are assumed to be at distinct nodes. The last step is the first one, at the beginning of which all the agents are at the same node. The last step consists in ensuring that there is no other agent in the graph, and all the agents declare simultaneously that the gathering is achieved at the end of the last step. All other steps allow to divide by 2 the number of nodes on which the agents are spread. More precisely, if ki denotes the number of nodes on which the agents are spread at the beginning of step I, then the algorithm executed by the agents during each step ensures that ki plus 1, the number of nodes on which are spread at the beginning of step I plus 1, is at most ki over 2. The algorithm executed at each step ensures that the agents at the same node at the beginning of a step stay together during most of it. Thus, Ki is the number of groups of agents left at the beginning of step I. At the beginning of each step, each agent knows how many agents there are in its current node, and thus how many agents are in its group. When, later during the step, there are more agents in its current node than there are in its group, the agent knows that its group has just met another one. Let's focus on the algorithm for one step and on the following basic idea. The agents execute subroutine exflow. During this execution, all the agents of the same group stay together. They interrupt this execution as soon as another group is met, that is, as soon as there are more agents in the current node than in the group. Then, they wait to allow some other groups to meet them easily. Executing this basic idea can lead to two different situations. Either at least one meeting occurs, or none occurs. In the first case, we can prove that the two groups actually meet while they are both executing the first part of exflow. At the end of this part, there are two types of groups. Those which have met at least one other group, and thus have started waiting, and those which still have to perform the second part of exflow. This part allows them to visit every node of a graph, and thus to meet some idle groups of the first type. Hence, in the first case, every group meets at least one other group by the end of the step. In the second case, we say that the groups are invisible to each other. We benefit from this property to emulate communication inside each group. The idea of emulating communication in our model is natural. However, it turns out to be very delicate to put in use. Indeed, without special care, one gets soon to a dangerous situation where communication movements of one group can interfere with communication movements of another closely located group. On top of this difficulty, we have another one. Movements of agents must serve to accomplish two different goals. One is to communicate with other agents, and the other is to travel in order to meet. Hence, we face the danger of traveling movements interfering with communication movements. This is why invisibility is so important. It prevents most interferences. The most interesting part of the rest of this presentation concerns the emulation of communication. But before that, I'm going to present a simplified version of the pseudocode executed at each step. The first two lines correspond to the basic idea presented in the previous slides. The instructions from line 4 to line 8 are executed only in the second case, when the groups are invisible to each other. Line 4 corresponds to the execution of a subroutine emulating communication, thanks to which, in every group, all agents learn the label of one member of the group, a leader, a local leader. Then, at line 5, in every group, all agents execute the state-of-the-art gathering algorithm as if they all had the same label as the leader in order to stay together and meet other groups. Putting aside some technical details, upon completion of line 5, either every group has met at least one other group, or we are sure that there is no other group to meet, and all agents can declare simultaneously that the gathering is achieved. I am now going to explain how our communication emulation subroutine works. First of all, since its main goal is to allow the transmission of one label per group, the label of the leader of the group, our subroutine only allows one agent per group to transmit its whole message. Note that this agent is chosen dynamically during the execution of the subroutine. It has not to be elected beforehand. The transmission occurs bit by bit. This table represents the instructions executed by every agent to transmit one bit. Every bit transmission is divided into two halves, and the behavior of the agent depends on its next bit to transmit. During the first half of the bit transmission, the agents with a 0 execute exflow while the others stay idle, and vice versa for the second half. Staying idle allows not to interfere with the agents which execute exflow, and this execution allows to count the agents in the group with the same bit to transmit. Let's assume that we have 4 agents. The blue one has to transmit 1, while the others have to transmit 0. Let's see how the transmission of 1 bit goes and what the agents learn. Let's assume that the yellow and green agents are one group and that the blue and red ones are another group. During the first half, the blue agent stays idle while the others visit the graph. The blue agent can be met only in this node. Moreover, thanks to invisibility, the red agent cannot meet the yellow and green ones. Remember, invisibility means that they don't meet when they execute explo. Hence, there are nodes in which the red agent is going to be alone and in which the yellow and green agents, which execute explo together, are going to be alone. They do not know in advance which nodes these are, but at the end of the execution of explo, they can compute how many agents in their group have the same bit to transmit as them. The second half is similar, but with roles exchanged. The blue agent executes explo, while the others stay idle. During the second half, the blue agent is alone in this node, for instance. Okay, let's now take a look at the computations performed by each agent at the end of the bit transmission in order to deduce which bit they understand as received and the impact on the transmission of the next bits. Each agent knows the number of agents in its group, as well as the minimum number of agents seen during its execution of explo. This second number is also the number of agents with the same bit in its group. They executed explo together, and there is at least one node in which there were only them. Each agent can easily deduce the number of agents of its group with the other bit. When all agents of the group try to transmit the same bit, then this bit is received. And if for both bits where agents try to transmit it in the group, then we arbitrarily choose that 0 is received. Hence, 1 can only be received if no agent in the group tries to transmit 0. The blue agent tried to transmit 1 and received 0. His bit is not the one received. The blue agent has been eliminated from the leader election. We can think of it as if there were a pool of candidates for the election, for being the agent whose whole label is transmitted to the group, and if the candidates were eliminated when a bit different from theirs is received. When an agent is eliminated from the election, it keeps executing the subroutine in order to learn the next bits, but in a passive stance. From now on, it always tries to transmit 1. In conclusion, I would like to remind you of our contributions. We prove that in order to gather, you don't need to chatter. More precisely, assuming that the agents are unable to communicate explicitly, but know the number of agents in their current node, we provided 2 deterministic gathering algorithms. The first one requires that all agents initially know a polynomial upper bound on the number of nodes, but is polynomial. The second algorithm requires no additional information, but has a larger complexity. As a byproduct, since our first algorithm relies on the emulation of communications which can also be viewed as an election, we propose algorithms for gossiping and leader election in our model. The main open question left by our work is whether there exists a deterministic polynomial gathering algorithm in this model requiring no additional information given to the agents. Thanks for watching the video.